Okay, grade 11, so we looked at Coulomb's law yesterday, just when we had two charges. Now that's way too easy. You might have noticed how easy that is. It's very unlikely you're going to run into a scenario where you only have two charges. That is far too easy for grade 11. So it's much more likely you'll have three charges, and they can either be arranged in a linear manner, so in a straight line, or they can be arranged sort of looking like a right angle triangle. So you can either have 3-point charges in a straight line, or you might have 3-point charges that are arranged sort of like a right angle triangle, if you can imagine that. Okay, so today we're going to look at the scenario where they're arranged in a linear manner. Now, in order to understand the section, understand how it works, firstly you have to understand that if I do have 3-point charges all in a row like this, that this charge A will experience an electrostatic force from B and also from C. And B will experience a force from A and also from C, and C will experience a force from A and also from B. So that means each one of these point charges is experiencing two electrostatic forces that result in the net force it's experiencing. Okay, now before we move on to the steps, I just want to remind you that electrostatic force is a force, and a force is a vector, and whenever you have vectors that are, whenever you've got multiple vectors and you want to find out what the overall vector is, remember that's just determining the resultant vector, which we did in maybe the first or second lesson of the year, here determining the resultant vector of vectors in 1 or 2 dimensions. So here where you've got it in a linear shape, that's only 1 dimension, makes life a little bit easy. So here, just a reminder, let's say I've got a vector pointing to the right and another vector pointing to the left. To find the resultant, we would just say, well, the length of that one minus the length of that one. Or if we had two pointing in the same direction, we would add them together, right? So that's basically the idea behind working out the electrostatic force experienced by one of our 3-point charges when they're arranged in a linear manner. We'll use Coulomb's law to determine the force on, let's say we're dealing with A, the force on A due to B, the force on A due to C. We could imagine it as a vector diagram where these are those two forces, and then just do vector addition to work out what the resultant force is, what the resultant vector is. Okay, now on your worksheet or on your notes, I've written down the steps for you of how I want you to set up your answers. Okay, so when you're setting up your answer, the first thing you need to do, and you don't have to write this down, you do this in your head, just make sure that you've done it, make sure that you're aware of it, is to determine the direction of each of the two forces. Okay, there will be two forces at play because we've got 3-point charges, and we'll be talking about one of the point charges, so let's say I'm interested in that one. It will experience a force from this charge and a force from that charge. So there will always be two forces. So determine the direction of each of the forces. Okay, make sure you know what direction they're going in, if it's going right or left or up or down or what it's doing. Depending on, and the way you make that decision is you base it on if the charges are positive versus negative, and therefore if they are attractive versus repulsive forces. Okay, so for example, if I had 3-point charges A, B, and C, and let's say I was interested in working out the net force on B, and A was positive and B was negative and C was negative. Okay, then to determine the direction of each of the forces B is experiencing, so B will experience a force from A and a force from C. The force it would experience from A, because they are oppositely charged, that means it's an attractive force, so that means B will be pulled to the left, right? So we can say that the force of A on B would be to the left, and then for C, these are both negative, which means it's a repulsive force, which means B would also be being pushed to the left from C. It would be pushed away from C. So we can also say that the force of C on B is also to the left. Okay, so you can all do that all in your head. You don't need to write it down, but just make sure you know which direction each of them are going in. Okay, then the next step, step 2. What have we written here? Pick a positive direction. This I do want you to write down. It's not worth a mark, but it's helpful for you to be able to refer back to. Okay, so you pick a positive direction. So you're going to write there somewhere, let right be positive or let left be positive. My cat is losing its mind. Sorry, I've got to let it out quick. Okay, sorry about that. So you pick a positive direction. You say let left be positive or let right be positive or whatever it is. Then step 3. Okay, we're going to use vector addition with Coulomb's law. Okay, to write out what the net force would be. So if net would equal the vector sum, so this is vector sum, hey, you don't just add, you decide based on the direction if you add or you subtract. So the vector sum of all of the forces on the point charge that you're interested in. Okay, so the net electrostatic force is the sum, vector sum of all the electrostatic forces on the charge that we're interested in. Okay, so here your plus, sorry, if it's in the positive direction, and minus if it's in the negative direction. Okay, and you don't just leave it like that. You would then expand so that you are using Coulomb's law. So this would be expanded to the sum of K Q1 Q2 over R squared. And you do that for each of them. Okay. And then second last step, sorry, you sub in your values. And step 5, you solve for the unknown. Now the unknown might not be F net. They might give you F net and ask you to determine the distance between two of the charges or the electrostatic charge on one of the charges. Okay, they can ask you to do that. Okay, so I'm going to pause you here and then we're going to do the examples that are on your worksheets because I don't want anybody to be at a disadvantage if they're unable to watch these videos. Okay guys, so here's your first question. We've got 3-point charges, A, B, and C. So here's A, B, and C. They've told us that A and B are 10 centimeters apart, B and C are 12 centimeters apart, and they've given us the charges on A, B, and C. Quick reminder, nanocoulombs, that is, so 1 nanocoulomb equals 1 times 10 to the millimicronano, negative 9 coulombs. Okay, so we use coulombs in Coulomb's law, not nanocoulombs. Okay, then they ask to determine the force experienced by B. So we are interested in B, which means the forces experienced by B will be due to A and due to C. There'll be 2 forces experienced by B. Okay, now the way we do this, first off, we determine which direction each of those 2 forces will be. So I'm going to do this graphically. The way I've done it on the notes is by writing it down, but I think it's easier to see it if it's graphically done. So the force of A on B, let's have a look here now. B is negative and A is positive, which means it's going to be an attractive force. So the force of A on B is going to want to pull B to the left, right? It's going to want to attract B to it. So the force of A on B is to the left. Okay, then let's look at the force of C on B. C is negative and B is also negative, which means that's a repulsive force, which means C will be pushing B away, which is also to the left. So the force of C on B is also left. Okay, next up we pick a positive direction. I'm stuck in my ways. I like to always just pick right as positive or up as positive, but these are both left. So if you want to say left as positive, go for it. Okay, I'm going to say let right be positive. Okay, and now we set up our vector addition. So we want the overall force experienced by B. So we can say F net, or you can say F B if you want to, I don't mind, I like F net. So the net force experienced by B is equal to the sum, the vector sum of the forces on B. Now we've got two forces on B. We've got the force of A on B and the force of C on B, and they are both to the left, and I've said right is positive. So that means both of these terms are going to be negative. Okay, and now we go and expand them using Coulomb's law. So F net equals negative K Q. Now look what I'm using here. Because this is the force of A on B, we use the charges of A and B over the distance between them squared, minus K. Now this is the force of C and B, so we use the charges of C and B over the distance between them squared. And we substitute in and we solve for what we want. So F net equals negative. K is 9 times 10 to the 9. Remember, when you substitute into Coulomb's law, you omit the sign of the charge, please. So QA is positive and QB is negative. Don't include those. It's just 4 and 7. Okay. Okay, so it's times 4, but it's not just 4. It's 4 nanocoulombs, which is 4 times 10 to the minus 9 coulombs. And 7 times 10 to the minus 9 over the distance between them squared. The distance between them is 10 centimeters. We don't use centimeters in Coulomb's law, we use meters, so unit conversion, 0.1 squared. And then our next one, minus K, which is 9 times 10 to the 9, times the charge on C, which is negative 4, but we don't include the sign, and then the charge on B, which is negative 7, but we don't include the sign, over the distance between them squared. That's in centimeters. I want it in meters, so it's 0.12 squared. And we stick this all in our calculator, and we get negative 4.27 times 10 to the negative, oh, that's tiny, negative 5. And then remember, always when you've worked out what your net or resultant vector is, look at your sign, rewrite it including the direction. So we never want a negative vector, you write it as a positive. Okay, so it's 4.27 times 10 to the negative 5 newtons. And that negative told us, I said right was positive, which means my net force is to the left. Okay. So that's how we do it. I'm going to do another one where it's like this, where we're finding out net force, but we're going to do it for charge C. Yeah, for charge C, and then we'll do one where they ask you to calculate something else. So same question, same scenario. I'm just going to erase A and write down question B for the same scenario, same point charges. Okay guys, so now I see you've fallen down a bit, sorry. Now we're interested in the net force experienced by charge C, that's the one on the far right. So we're now interested in this one, okay, and we're going to deal with it the same way. So first off, make sure you know which direction each of the forces are in. So I'm going to write it down, the force of A on C, and then the force of B on C. Okay, so the force of A on C, these are oppositely charged, which means QA is going to attract QC. It's an attractive force, which means QC's force from A is going to be to the left. It's pulling it left. So the force of A on C is to the left. And we're going to do the same thing for the force of B on C. B is negative and C is also negative, which means this is a repulsive force, which means QC is going to want to move away from QB, which is to the right. So the force of QB on QC is to the right. Okay, now again, we pick a positive direction, so I'm going to say let right be positive. Okay, and we go ahead and do our vector addition. So the net force experienced on C is equal to the vector sum of all the forces C is experiencing, which is the force from A and the force from B. The force from A is negative because it's to the left, and the force from B is positive because it's to the right. Okay, and now we expand those and substitute. So F net equals negative K QA and QC over R squared plus K QB and QC. Okay, and now we can substitute in and solve. So our net force is equal to negative 9 times 10 to the 9. QA and QC are 4 and 4. We exclude the sign of the charges, sorry, so it's only the number. So it's 4 times 10 to the minus 9 and 4 times 10 to the minus 9. And now the distance between QA and QC is this whole distance. So it's 10 centimeters and 12 centimeters. So that's going to be 22 centimeters, which we convert to meters, 0.22 squared, plus our proportionality constant, which is 9 times 10 to the 9. The charges on B and C are 7 and 4. We exclude the signs. Okay, over the distance between them squared, from QB to QC, it's 12 centimeters, so 0.12 meters. Guys, please don't forget to square your denominator. That's one thing I see happen quite often. Silly mistake. Okay, don't forget to square it. And when we do that calculation, we get 1.45 times 10 to the negative 5. Okay, now this is already positive, so we can say if it's positive, it means it's right. Okay, and that is it. That's all we have to do there. Determine the net force experienced. This is please how I want you to set it up. You might see it set up slightly differently by different teachers. The reason I want you to set it up like this is because when you've got it in this form, it doesn't matter what they ask you to solve for. You can solve for anything. If you do it, some teachers want you to do it separately. So first find the force of A on C, then find the force of B on C, then do vector addition. The problem with that is that only works if they ask you to find net force. As soon as they've asked you to find something else, then you're going to be in a bit of you're going to have a bit of a problem. Okay, so rather please set it up like this so you have one equation with everything in it. Okay, so I'm going to pause you there and I'm going to show you a scenario where they ask you to find something other than the net force. Okay guys, so we've got 3 charges, A, B, and C. They tell us the distance between A and B is 3 meters. The distance between B and C is x meters. We know the value of the charge on each of them. And they also tell us that F net on A, the net force experienced by A, is 1 times 10 to the negative 8 newtons to the left. And we need to determine x, the distance between B and C. Okay, so we've got 3-point charges in a row. We need to find the distance between 2 of them. We're going to set it up just like we did the previous questions. Okay, so first off, the direction of the forces. So we're talking about F net on A. Okay, so that means A is going to experience a force from B, so force of B on A, and from C, so the force of C on A. Okay, B's force on A, they're both positive, so B's force on A is going to be a repulsive force, which means it's going to push A away. It's going to push it to the left. So the force of B on A is to the left. Okay, force of C on A, C is negative and A is positive, so it's an attractive force, which means A is going to want to move to the right, closer to C. So the force from C on A is to the right. Okay, now again, we pick a positive direction. I like saying right is positive. Okay, so let right be positive. And now we set it up just like we did. So we're going to say F net is equal to, okay, the force of B on A is left, so it's negative force of B on A. The force of C on A is right, so that's positive. And now we expand. So F net equals negative K QB QA over R squared plus K QC QA over R squared. Okay, so we just expand. Because it's the force of B on A, we use the charges of B and A. Because this is the force of C on A, we use the charges of C and A. Okay. Now we substitute in what we know. Now we don't know this distance. We don't know the distance from B to C. This R over here. Oh, wait. It's going to affect this R over here. Okay, so, but we do know one thing. We know that the net force on A is 1 times 10 to the negative 8 left. So we can substitute this in for F net, and it's left, which means I'm subbing in a negative number. Negative 1 times 10 to the negative 8 equals negative. K is 9 times 10 to the 9. The charge on B is 6 nanocoulombs, so it's 6 times 10 to the negative 9. The charge on A is 2 nanocoulombs, and the distance between them is 3 meters squared. Plus, K is 9 times 10 to the 9. The charge on C is 4 nanocoulombs. Remember, you only use the magnitude of that charge, not its sign. And then the charge on A is 2 nanocoulombs. All over the distance between A and C squared. Now the distance from A to C is 3 plus x. Luckily that's already in meters. So 3 plus x squared. And now we solve for x. Okay, a little bit tricky. So first off, what I'm going to do is I'm going to isolate the term that has my variable in it. Okay, so I'm going to take this term across and change it to a plus sign. Okay, and I'm actually going to type that in on my calculator. Negative 1 times 10 to the negative 8 plus this fraction, and simplify that and see what I get. And I think I actually did do it on this worksheet. Makes life a little bit easier. Okay, so we get 2 times 10 to the negative 9 equals this fraction. I can simplify the top of that fraction. And when I simplify the top of that fraction, I get 7,2 times 10 to the minus 8. Sorry, my eyes are not very good. Over my denominator, which is 3 plus x squared. Okay, now it's up to you how you like to solve equations where your denominator has your variable in it or is your variable. So my preference is, I know that if I have, let's actually use it with variables. Okay, if I have fractions like this, if I have x over y equals a over b, and I want to isolate b, okay, I know that I can cross multiply that, so I'll have bx equals ay, and then I divide both sides by x to get my b alone, so b equals ay over x. Okay, so what we've done in this case is we've actually just taken this numerator and divided this side by that numerator. I don't think I'm explaining this very well. Okay, let's rather look at a scenario where it looks closer to that. Okay, so let's say we have x equals a over b. Okay, that means x over 1, right? We cross multiply, we'll have bx equals a. I want to get b by itself, so I divide both sides by x. I'll have b is equal to a over x. So do you see, basically you can look at the scenario. It's going to do this every time you do it. It's going to have the same pattern, where this numerator stays the numerator, and this isolated variable becomes the denominator. Okay, so it's going to do that every time. So I can just go ahead and straight away do that. I'm going to say, I know that my original denominator, if I want to write it isolated, 3 plus x squared, I can write my original numerator stays my numerator, so that's 7,2 times 10 to the minus 8 over the thing that was originally isolated, so 2 times 10 to the minus 9. Okay, does that make sense? If you don't like doing it like that, that's fine. You can actually cross multiply here and work it out the same way. You'll get to the same point. Okay, now we can simplify the left-hand side. I think I'm running out of vertical space. I think you can only see up to like here somewhere on the board. So I'm going to start working sideways. So we get 3 plus x squared equals, that fraction simplifies to 36. That's pretty cool. Now we square root both sides to get rid of the squared. and we get 3 plus x equals 6. Okay, if this were maths, your maths teacher would be panicking right now because technically we've actually lost one of the possible solutions here. This 3 plus x could equal 6, or 3 plus x could equal negative 6, okay? But we're talking about a distance here. It's a scalar. We're not going to have the negative version of the answer, okay? So we only have to worry about the positive version. And now we solve for x. We hop our 3 over and subtract it, and we get x is equal to 3 meters. And that's it. Okay, we are done. Yeah, so I'm going to send this to you. I'm going to send you guys the worksheet for this section, or for this, for this scenario when you've got 3 charges in a linear arrangement. It's not that bad. I'm hoping you can code. It looks scary, but I promise you it really isn't. It's just Coulomb's law and vector addition. That's it. Okay, so please do let me know if you get stuck, if anything is confusing you, and we are nearly there, guys. We're nearly through this.